Think about it for a second. The Wi-Fi that's probably bringing this to you right now, the GPS that gets you home, the music streaming in your car, we are just surrounded by these invisible signals flying through the air. And it feels like total magic, but it's not. It's pure physics. Today, we're going to pull back the curtain on the unsung hero of our wireless world, the antenna.
So how does it actually work? How do you take an electrical signal, something that's supposed to be trapped inside a wire, and somehow convince it to just leap out into the air and travel for miles? What's the fundamental secret that turns a boring old piece of metal into an antenna?
Well, to figure out how antennas actually work, we first have to wrap our heads around the problem they're designed to solve. It's what I like to call the signals escape problem. Because, as it turns out, you can't just use any old piece of wire.
Okay, so here's the absolute key difference. If you take a simple, closed loop of wire and run a current through it, you do create a fluctuating electromagnetic field, but that field is kind of trapped. It just clings to the wire and doesn't really go anywhere, which makes it totally useless for communication. An antenna's real job is to create a wave that actually detaches and travels away, a wave that propagates.
So the big question is, how do we set that wave free? Well, the answer is found in some really beautiful fundamental physics. This, right here, is the secret of propagation.
Believe it or not, everything starts with this one simple concept, the electric dipole. It's really just a positive charge and a negative charge, separated by a tiny bit of distance. This simple little setup is the engine that drives basically every antenna in existence.
All right, so when it's just sitting there, not moving, these two opposite charges create an invisible line of force between them. That's an electric field. The best way to picture it is like a tiny invisible rubber band that's stretched out between those 2 points.
But what happens when we make these charges move? Let's say we make them oscillate, just wiggle back and forth really fast. Well, that electric field, that rubber band, it doesn't just instantly snap to the new position. It kind of has a memory effect. The field line gets stretched and distorted, creating this kink as it tries to keep up with the moving charges.
And here is the magic moment. If you oscillate those charges fast enough, that kink in the field line gets stretched out so much that it actually snaps off. It becomes its own self-sustaining electromagnetic wave that just shoots off into space at the speed of light. That is our escaped signal.
Okay, so that's the cool physics part. But how do we take this idea and turn it into a real thing, a real piece of metal? How do we create this oscillating dipole in the real world? Well, it's actually much, much simpler than you might think.
You literally just start with a simple conducting rod. Then, you apply a rapidly changing voltage right in the middle. This voltage pushes and pulls on all the free electrons in the metal. It forces them to pile up on one end of the rod, making that end negatively charged, which of course leaves the other end positively charged. And boom, there it is, a dipole. And since the voltage is oscillating back and forth, the charges shuttle back and forth, creating the exact same wave-detaching effect we just saw.
Now, for this whole thing to work really efficiently, there's a kind of golden rule. The antenna's physical length needs to be tuned to the signal. Specifically, it should be half of the signal's wavelength. This is the simple reason why the antenna for your Wi-Fi router is just a few inches long, but an old AM radio tower has to be hundreds of feet tall. Different frequencies mean different wavelengths, which means different sized antennas.
All right, so we've cracked the code on how antennas transmit signals. But what about receiving them? How does your car radio antenna pluck one single station out of the air? The beautiful thing is, it's the exact same piece of hardware, just working in reverse.
This is all thanks to something called the principle of reciprocity. And it's actually super intuitive. An antenna that's good at sending is also good at receiving. When a propagating wave, say from a radio station, hits your car's antenna, its electric field pushes and pulls on the electrons inside the metal. This makes those electrons start to oscillate, which creates a tiny fluctuating voltage at the center of the antenna. And that voltage, that's the received signal, which your radio then just amplifies and turns into sound.
So now that we know the secret, that it's all just about creating an oscillating dipole, let's go on a little tour and spot some of the antennas you probably see every single day, the antennas out in the wild.
You really do see these everywhere. That classic rooftop TV antenna, the Yagi-Uda, it's all about being directional. Those extra metal rods basically act like lenses to focus a distant signal onto the main receiving part. A satellite dish? That just takes the idea to an extreme. It's a giant curved mirror for catching incredibly faint signals from space. And then deep inside your smartphone, there's a patch antenna, a tiny metallic square, perfectly sized to be half the wavelength of a cell or Wi-Fi signal. It just proves that the same principle works on a massive scale
and on a miniature one.
And, that really is the key takeaway. Whether it's a gigantic dish or a teeny tiny patch, they are all just clever ways to harness the exact same physical phenomenon, creating an oscillating charge that either launches a wave or gets moved by one. The source material puts it perfectly. The simple dipole antenna also produces the same phenomenon, and wave propagation occurs.
So, the secret to sending a signal through thin air, it's not magic after all. It's just about getting charges to wiggle in the right way. And that kind of leaves us with a final thought. Now that we know the fundamental principle is actually so simple, what will the next generation of antennas look like? Could they be woven into our clothes? Or maybe even painted onto walls, hiding in plain sight? The physics definitely allows for it.